Short-circuit current waveform. Introduction. The shape of the short-circuit current waveform depends upon the power generation capacity, network parameters, location of fault, and instant of the occurrence of fault. The amplitude, asymmetry, and duration of the prospective fault current is important in establishing the suitability of connected equipment such as switchgear, instrument transformers, busbar systems, cables, setting of protective relays, etc. For the sake of ease of explanation and understanding, consider a single phase line subjected to a short circuit. When a fault occurs on a single phase line, the short circuit currents will be much larger than the rated current. The power factor of the fault current will depend on the impedance behind the fault. The fault current wave, more often than not, will not be symmetrical. It depends on the point on a wave at which the fault occurs and the power factor of impedance up to the fault location. On an unloaded line, the current has to start from zero and reach a maximum during its first peak. The offset in the current wave can best be analyzed by superimposing symmetrical phase alternating current on a decaying direct current. The degree of asymmetry will depend upon the magnitude of the direct current. The time duration of asymmetry will depend upon the ratio of inductance to resistance of the fault circuit. The peak value of the fault current will depend upon the impedance and the power factor. The maximum peak will correspond to zero power factor reaching a theoretical maximum of 2.828 and the minimum at unity power factor at 1.414. The decay time from peak asymmetry to symmetry will depend upon the time constant dictated by the ratio of inductance to resistance of the fault circuit. The multiplication factor for the peak current, for the other power factors, is detailed in the table. The magnitude and asymmetry of a short-circuit current waveform in a network will depend upon several factors. Type of fault, load before fault, point on wave of occurrence of fault, fault location and source impedance. Type of fault. The fault in a three-phase system can be categorized as line to ground, line to line, double line to ground, triple line and triple line to ground fault. The magnitude of the steady-state fault current will depend upon the equivalent source voltage and combined series impedance through which the fault current flows. Line-to-ground faults are most common in any network. In an LV system, the voltage across the arc can be significant, compared to the rated voltage, and consequently, the fault current will be much lower than a prospective fault current with a bolted earth connection. For medium and high voltage systems, the voltage across the arc is of little significance. In a network, a line-to-ground fault can result in a double line-to-ground fault or even a triple line-to-ground fault due to the dispersion of ionized air. Load before fault. In most of the situations, the magnitude of the fault current will be far more than the load current before the occurrence of the fault. The magnitude and power factor of the load will have only a marginal impact on the DC component of the fault current. Point on wave of occurrence of a fault. The instance of the occurrence of the fault on an impressed voltage wave will determine the magnitude of the DC component of the current. Fault location and source impedance. The fault can occur at any location of the network comprising generators, transformers, overhead line, cables, and other series elements such as reactors. The intensity of the fault current will depend upon the voltage and impedance of the upstream elements, including the source impedance rationalized on a unit system. From the viewpoint of the nature of fault current waveform, the locations can be classified as those that are farther away from the generator and those that are near to a generator. Fault simulation. Let a sinusoidal source having an RMS value E be switched on to a load Z having a power factor. Since the instantaneous current has to be zero at time zero, it will generate a DC component that will decay exponentially with a time constant 2 defined by the circuit parameters of ratio of inductance to resistance. The DC component will depend upon the power factor and the point on the wave at the instant of short circuit. Fault away from the generator. This is a condition where the series impedance between the generator terminals and the location of the fault is significantly higher than the generator impedance. Let the fault be initiated at an instant when the voltage wave has a magnitude corresponding to an angle alpha in the equation. The instantaneous value of the fault current will be proportional to the applied voltage, the resistive and inductive component of the impedance, and point on wave of occurrence of fault. The instantaneous value of the applied voltage at an angle alpha and the corresponding instantaneous value of the current is displayed. From the formula for the instantaneous value of current, it is evident that the waveform will have total symmetry when alpha, the initiation of the fault on voltage wave, and phi, the power factor angle of the load are 90 degrees. Implying that the short-circuit current waveform will be symmetrical when the fault occurs at the instant when voltage is at the peak on a purely inductive circuit. The waveform will have maximum asymmetry when alpha, the initiation of the fault on voltage wave, is 0 and phi, the power factor angle of the load, is 90 degrees. Implying that the short-circuit current waveform will have maximum asymmetry when the fault occurs at the instant of voltage 0 crossing on a purely inductive circuit. Fault near the generator. This is a condition where the fault occurs in the very close proximity of the generator terminals. A connection between the generator and generator transformer has several tap-offs to feed auxiliaries through auxiliary transformers, to static excitation system, and to surge protection, voltage transformer cubicles. Any fault on the terminal equipment at the generation voltage will fall under this category. To analyze the waveform, the source voltage can be kept constant and a variable reactance of the generator can be considered to be a combination of a subtransient reactance, X"D, is associated with a time constant, T"D. This phenomenon is attributed to the presence of damper winding on the poles of an alternator. The subtransient reactance may vary from 10% to 20% for turbo alternator and 15% to 20% for a salient pole machine. The subtransient time constant is of the order of 20 milliseconds. A transient reactance, X"D, is associated with a time constant T"D. This phenomenon is attributed to the presence of field winding of the alternator. The transient reactance may vary from 15% to 25% for turbo alternator and 25% to 35% for a salient pole machine. The transient time constant is of the order of 100 to 500 milliseconds. A steady-state or synchronous reactance, XD, is attributable to the armature winding. The steady-state reactance may vary from 150% to 230% for turbo alternator and 70% to 130% for a salient pole machine. A periodic component with a time constant TA is approximately 100 milliseconds. The instantaneous value of the fault current as a function of the generator parameters is governed by the displayed equation. The parameters include subtransient, transient, and steady-state reactances with associated time constants. Generator terminals are connected to the step-up transformer by a metal-enclosed, air-insulated busbar system. These are isolated phase bus for large capacity units and segregated phase bus for smaller units. These connections incorporate current transformers for metering, protection and control. A generator circuit breakers may also be installed, if specified. The magnetic parameters of the current transformers will depend upon the magnitude of the asymmetry of the current waveform. The zero crossing of the instantaneous value of current may take more than one cycle depending upon the generator parameters. Consequently, the generator circuit breakers are designed to cater to longer arcing time. Fault current terminology. A fault current in a three-phase AC network is transient, in nature, until it is cleared by a protective device such as a circuit breaker. The current waveform comprises a combination of a decaying DC component of the current and an AC component that eventually stabilizes as a symmetrical wave before being isolated from the faulty network. The relationship between the RMS value of the asymmetrical AC current, symmetrical AC current and the DC current is governed by the displayed equation. For a fault at a location far removed from the generator, IAC will be constant and IDC will decay with a fixed time constant. However, for a fault close to the generator, IAC will decrease in magnitude and stabilize while IDC will decay with a varying time constant. For the maximum asymmetrical current, the peak value obtained in the first quarter of the cycle of IAC and corresponding IDC shall be considered. For a three-phase short circuit, it is evident that the waveform of the current in the three phases will be different. While testing for the short circuit withstand capability of a busbar system in a test laboratory, it is the practice to identify the phase that needs to experience the specified instantaneous peak current. Thank you. For a comprehensive understanding of the theory and practices of busbar systems, it is advisable to read the book An Introduction to Busbar Systems, where contents are organized in a sequence for ease of reading and facilitates cross-reference. Please procure a copy of the book with a requisition to Bala at busbarsystems.net.